This is a video on Newton's second law of motion. This is our learning target number 9 for this unit. Newton's second law just says that the net force on an object is equal to the product of its acceleration and its mass. That's just a long, fancy way of saying that force is equal to mass times acceleration. F equals ma. What Newton's really saying with this equation is that there is a relationship between those three variables, force, mass, and acceleration. For example, if the force goes up, the acceleration is going to go down, assuming that mass is constant. If you hold force constant, then if the mass goes up, acceleration is going to go down. If you recall Newton's first law talked about object maintaining constant velocity unless it was acted upon by an unbalanced force. Whenever that unbalanced force acts on an object, we know that the object's motion is going to change. Newton's second law just quantifies the change. So if an unbalanced force of x is applied to a mass of y, the acceleration is going to be z. Learning target number 10 is to be able to use that equation F equals ma to solve for either force, mass, or acceleration. And we have another triangle that we can use. Just remember that force is always going to go at the top of the triangle. If you recall from earlier unit, we defined the Newton as a unit of weight or force. So whenever we're dealing with newtons, we have to make sure that we're working in kilograms and that our acceleration is in meters per second squared. And 1 newton is really just the amount of force that's required to lift 1 kilogram at a rate of 1 meter per second every second. Here's an example of using Newton's second law. If you are given 2 of the 3 variables, you should be able to solve for the third. So if we're given a mass of 10 kilograms and an acceleration of 3 meters per second squared, we should be able to calculate the force. Equation is F equals ma. So when we plug our numbers in, we have force equal to 10 kilograms times 3 meters per second squared. When you do the math, the force is equal to 30. Units left are kilograms meters per second squared, and a kilogram into meter per second squared is a newton. So our answer is force is equal to 30 newtons. Another example, if we're given force and acceleration, we should be able to calculate mass. Just have to rearrange the equation, cover up the m in the triangle, and you have F divided by a, force divided by acceleration. We plug the numbers in. Mass is 20 newtons divided by 4 meters per second squared, and we end up with a mass of 5 kilograms. Just remember, when you're working in newtons, mass is always going to be kilograms. Third example is solving for acceleration, given the force and the mass. Again, cover up the a, and you have force over mass. Plugging the numbers in, 8 newtons divided by 4 kilograms gives us an acceleration of 2, and the units are meters per second squared. If you recall again from an earlier unit, we talked about weight being a force that's due to an acceleration due to gravity. So really weight is just a special force due to a special acceleration. The equations are almost identical. We just substitute the W for the force. And instead of a general acceleration, we have a very specific acceleration, G, that's due to gravity. So question, which one of the objects is going to hit the ground first? The feather or the elephant? We can have the same debate about who was right, Aristotle or Galileo. Aristotle said the heavier object is going to strive to get to its resting place faster than the light one. Galileo says that it doesn't matter what the object weighs or how much mass the object has, that they're both going to accelerate at the same rate and hit the ground at the exact same time. We can solve the debate using Newton's first and second laws now. First law talked about that unbalanced force, and then we described some of the possible unbalanced forces that might act on an object. We came up with three natural forces: friction, air resistance, and gravity. We're going to be dealing with air resistance and gravity when we're dealing with falling bodies. So we say an object is in free fall when the only force acting on it is gravity, which never really happens because we're always going to have some air resistance, so technically nothing's ever in free fall, but let's just assume the only force acting on an object is gravity. When gravity acts on that object, it's going to make the object accelerate because gravity is an unbalanced force. It's going to cause all objects to accelerate at 9.8 meters per second squared here on Earth. But there's a difference between the ideal conditions in the real world. We also know that air resistance is going to act on the falling object, and that's going to change its acceleration. So as each little air particle hits that falling object, it's going to slow that object down just a little bit. And the more particles an object hits every second, the more it's going to slow down. So the greater the surface area, the greater the air resistance. Great example is skydiving. The skydiver wants to slow down. He spreads his arms and legs out, tries to catch as much air as possible. He really wants to slow down. He opens his parachute and really increases his surface area. The second thing that affects air resistance is the velocity. As you start going faster, you're going to hit more and more air particles every second. You know this if you've ever stuck your hand outside of a window of a moving car. When you're at a stop sign, there's no pressure on your hand, but as you speed up, you feel more and more pressure. It's because you're getting hit by more and more air particles. So air resistance gradually lowers the net force that acts on an object. And eventually that air resistance is going to equal that force of gravity, and we're going to have balanced forces. Once we have balanced forces, there's no more acceleration. So the object just is going to continue to fall at a constant velocity. We call that terminal velocity, the greatest velocity that a falling object ever reaches. When the objects first begin to fall, they all have that same force to mass ratio. So they all accelerate at 9.8 meters per second squared. But as air resistance increases, the net force decreases really, really quickly for light objects. And it takes a really, really long time to decrease for heavy objects. In the feather versus elephant example, at time 0, both of those objects are accelerating at the same rate, 9.8 meters per second squared. They have the same net force to mass ratio, so they're going to accelerate at the same rate. After 1 second, feather meets a little bit of air resistance, and its acceleration drops to, let's say, 4 meters per second squared. In that same 1 second, the elephant encounters some air resistance, but its net force doesn't decrease nearly as much, so its acceleration might only drop to, say, 9.7 meters per second squared. So you can see already the elephant's winning the race. It's a much higher net force to mass ratio. After 2 seconds, the feather that's falling has a force of air resistance that has balanced out the weight of the feather, so its acceleration is down to 0. The elephant, after 2 seconds, does encounter some air resistance, but again, it has a really big net force still, so its acceleration might only drop to 9.6 meters per second squared. So the feather now has balanced forces acting on it, while the elephant still has unbalanced forces acting on it. feather has stopped accelerating. The elephant is going to continue to accelerate. So the feather continues to fall at a slow, constant speed now. Balanced force is acting on it. The elephant is going to continue to speed up for a long, long time.